Hello, hello. Hope I'm audible. Okay, so today we are going to read a paper which is towards monosemanticity. So give me 1 second. So in the last stream, we were reading a paper and we didn't complete reading the paper. But I kind of don't want to continue that today. I want to read this paper, this one, towards monosemanticity, decomposing a language model with dictionary learning. So my college project is kind of related with this paper, so I want to read this in very depth, in really high depth. So yeah, let's start reading. So we'll start reading in the okay, that's kind of cool. You get this results in the beginning. Okay, we'll start reading, right? So before that, just ensuring that everything is cool. Is my audio low? Probably not. Hopefully not. So yeah. But before reading this, I kind of want to read like the summary of this paper. Summarize the paper. Even before that, I want to read the like abstract and the summary and this result. Right, let's skim through the paper. Right, stage one reading. Right, towards monosemanticity. Okay. So using a sparse autoencoder, we extract large number of interpretable features from a one-layer transformer. Okay. Then I think there's a second part to this paper, which is like scaling this thing. Wait, where is the paper? Yeah, this one. Scaling monosemanticity. Extract the interpretable feature from Claude 3 Sonnet. So this paper probably discuss about the idea of and the idea, and this paper discuss about scaling the idea. At least that's my hope. So let's skim through the whole concept. What are these? I don't know what these are. I kind of open this and I have no idea what this is. We'll look into it. We'll look into it. Yeah. Let's first start with the summary probably. Since my okay, the paper on semanticity represents a novel approach to understanding and decomposing the internal representation of a language model using dictionary learning techniques. Here are the key points. Core concept. They apply dictionary learning to activations. Okay. Main finding, they successfully identify interpretable features. Okay. Many features correspond to specific linguistic patterns or concepts. A better practical application, better understanding. Okay. Kind of wanted. Is there some like things like these? Research paper. Meh, maybe not. Wow. Right. I'm going to give the same thing to this ChatGPT, and probably ChatGPT will summarize it better. Okay, paper investigate methods to better understand and interpret internal mechanism of LLMs. Specifically, it aims to address the challenge of aligning behavior of language model with human intuition by promoting monosemanticity. Okay. The authors propose using dictionary learning techniques to decompose activation vectors in LLMs into interpretable and sparse representations. Okay. So we somehow convert the activation inside an LLM to a interpretable representation. Then we map this representation to useful features. Okay. The paper demonstrates that sparse decompositions reveal more interpretable structures than all with the dictionary atom. Okay, promoting. Okay. What is monosemanticity? It is a property of a neuron or a feature in a model having a single clear interpretable meaning. Okay. So being monosemantic means that a neuron does a single thing, right? So MLP in AI. Huh. Okay, weird. So each neuron means like one thing. That's probably it. That's probably what monosemanticity means. Okay. A monosemantic compound. Oh, I kind of want to make a summary, right? So, reading research paper. We go make a new one. Now we want to make a new folder. 25. Monosemanticity. Main.py, I guess. Okay. A monosemantic component responds consistently to one type of input or encodes one specific concept, making it easy to understand and predict the behavior. Okay, nice. Oh, main.py. I wanted not main.py. I wanted main.md. Okay, nice. Unambiguous per functionality. No. Okay, okay. Right. What is dictionary learning? It is a machine learning technique used to represent data as sparse combination of basis elements, often referred to as atoms, which forms a dictionary. The goal is to learn the basis element in a way that the data can be reconstructed accurately by using few atoms as possible. Okay, so probably we represent what? I don't know. Mhm. Machine learning techniques used to represent data as a sparse combination of basis elements. Uh, your example. Imagine you have a grayscale image and you want to represent each patch as the combination of basic patterns. Dictionary learning find these patterns and the sparse representation for reconstruction. Okay. the three image patches. Dictionaries updated learning key patterns such as vertical lines, horizontal lines, okay, sparse. Okay, so dictionary learning is something that like what converts a non-interpretable what's it called data into combination of basis elements. Okay, we'll I think we'll get more when we read the paper. It's fine, it's fine. And I'm just quick. So this is the name of the paper by Anthropic. Oh, it's 2021. It's 2023, man. What do you mean? Okay. Right. Mechanistic interpretability seeks to understand neural networks by breaking them into components that are more easily understood than the whole. By understanding the function of each component and how they interact, we hope to be able to reason about the behavior of the entire network. By understanding the function of each component and how they interact, we hope we will be able, okay, yeah, sure. The first step, no, hmm. The first step in this program is to identify correct component and analyze. Analyze. Mhm. Okay. In this paper, we use weak dictionary learning algorithm called a sparse. Oh, sparse autoencoder is a dictionary learning algorithm. Oh, yes. So sparse autoencoders learns them. Okay, for those who don't know what sparse autoencoder is, sparse auto. I mean, we'll ask ChatGPT. Sparse autoencoder. It is a type of neural network designed to learn compress the representation of input data by promoting sparsity in hidden layers. Not really. That is sparse auto. Oh, I assume sparse autoencoder. My bad. Okay, okay, okay. So we'll do this too. This is a sparse autoencoder. So this is it. So when you give an input, the sparse autoencoder. This is a sparse autoencoder. So sparse autoencoder tries to reconstruct the input as the output. So it uses like this one. This is a sparse layer. So this ideally is a very big layer, and many of the neurons are like sparse, which is zero, not eight, or something like that. So conceptually, this sparse autoencoder, or in short, Psi. So it will what do you call it? It will reconstruct this input as the output, but at the same time the data will the representation will be sparse. So hopefully, instead of like trying to understand this data or this data, we can understand how this is formed or some or anything like that using this one, this data, this hidden layer, the sparse hidden layer. So that's a concept. I don't know. Or at least that's what I think the concept is. Okay. So psi is the we use a weak dictionary learning algorithm called a psi to generate learned features from the trained model that offers a more monosemantic unit of analysis. Why can't I read analysis today? Than the model's neurons themselves. Okay, sure. The goal of this paper is to provide a detailed demonstration of sparse autoencoder compellingly succeeding at the goals of extracting interpretable features from superposition and enabling basic circuit analysis. Concretely, we take a one-layer transformer with a fundamental neuron MLP layer and decompose the MLP activation into relatively interpretable features. Okay, sure. Sparse summary. Sparse autoencoder extracts relatively monosemantic features. Okay, that's a summary. Okay, that's happy news. Uh, Next, we provide four different evidence for few features varying in specific context. Moreover, the last three analysis, moreover, the last three analysis show that the most learned features are interpretable. They produce interpretable features that are effectively visible in neuron bases. Sparse autoencoder features can be used to intervene on and steer transformer generation. Okay. Sparse autoencoder produce relatively universal features. Oh, apply to different transformer language model produce mostly similar features. Nice. Features appear to split as we increase autoencoder size. Nice. When gradually increasing the width of the autoencoder from 512 number of neurons to like 100,000 basically, we find the features which naturally fit together into families. Just 512 features can represent 10,000 of features. Despite the MLP layer being very small, we continue to find that new features as a scale of sparse autoencoder. Feature connect finite state automated like system that implement complex behavior. Okay. Hmm. Problem setup. A key challenge to our agenda of reverse engineering a neural network is the curse of dimensionality. As we study our larger model, the volume of the latent space represents the model's internal state that we need to interpret grows exponentially. We don't currently see a way to understand such or enumerate such a space unless it can be decomposed into independent components, each of which we can understand on its own. Our goal is to decompose MLP activation with sparse over complete autoencoder. So this is a this is a transformer layer, transformers. We take in the activation from after the MLP layers, before the unembedding layer, and apply a psi here, which can be 512 to this much in length. Features as a decomposition. If linear directions are interpretable, it's natural to think about the basic set of meaningful direction. In a sparse encoder setup, the feature activation or the output of the encoder, okay. Superposition hypothesis. To see the superposition, to see how the decomposition relates to superposition, recall what the superposition hypothesis postulates. Want to represent more features? Then they have neurons. I mean, I don't know. What makes a good decomposition? Why not use architecture approaches? Hmm. Using sparse order and gun to find good decompositions. Why sparseness? My idea is clear, right? Using sparse order and gun to find good decompositions. There's a good standard hypothesis that natural item variable in the world are sparse. Hmm. Although we have limited understanding of the features that exist in the language model, we is we are suggestive of highly sparse variables. Sparse order and gun setup. We briefly overview architecture and training of sparse order and gun here and provide further details of the further details down there. Our sparse order and gun is a model with bias as the input, a linear layer with the bias and the relief. Time on we found that the bias term were quite important. Yeah, what happened? Uh, we find that the autoencoder use add optimizer to reconstruct MLP activation of a transform model. Uh-huh. In training the autoencoder, we found a couple of principles to be quite important. First, scale really matters. Second, we found that the course of training some neurons cease to activate. Okay, how can we tell if the autoencoder is working? Usually, machine learning, we can quite easily tell if a method is working by looking at the easily measured unit like class. Unfortunately, we spent quite some time searching for equal metrics to guide our efforts here. Unfortunately, we are yet to find anything satisfactory. We begin looking for information-based metrics so that we can say in some sense that the best factorization is one that minimizes started information of the cotton data. Unfortunately, the total information did not generally correlate with the subjective feature. Okay. And inspection, feature density, reconstruction loss, time models. One letter song we are studying. Hmm. Notion of for features. Interface for exploring features. A detailed investigation of individual features. Okay. Man, I think I will read the paper the next tomorrow or something, or maybe even today, later. We'll just skim it now, right now. The features are a neuron. Oh, the feature seems rather monosemantic, but some models have relatively monosemantic neuron. Hmm. It's a really long paper, man. Man, the paper's so long. How interpretable is the typical feature? We use three different methods to analyze how interpretable a typical feature is. All three approaches find features are much more interpretable than neurons. Hmm. Automated interpretability. Logic weights. How much of the model does our interpretation explain? We now turn to the question that we are least able to answer. To what extent do these seemingly interpretable features represent the full story of the MLP? One could imagine posing the question in a variety of ways. What fraction of the MLP loss contribution have we made interpretable? How much of the model behavior can we understand? If there really are some discrete set of true features, what fractions have we discovered? One way to partly get at this question is ask how many of the loss is explained by our features. For S-1, we run the focused most on the paper. So, okay. In principle, one could use automated interpretability to produce a better measure here, replacing annotations with those predicted from explanations. Do features tell us about the model or data? That's interesting question. Yeah, basically both. Bit of both. To assess the effect of data as a correlation on the interpretability of feature activation, we run dictionary learning. I don't understand what I don't know what the word means. Phenomenology is a philosophy and research method that studies the human experience. Uh-huh. When trying about the feature, we found the apparent clusters. For instance, we observe that the above multiple base 64 features. Okay. Okay. We see clusters. Uh, Warning, I'm going to deactivate dark mode, clusterize. Okay. Hmm. They appear to be separated. I think that's what they are trying to get, right? We conjure that there is some idealized set of features that dictionary learning would return if we provided with unlimited dictionary size. In this picture, the reason the dictionary vectors have conceptually similar features are similar is that they are likely to produce more similar behavior in the model. Mathematics and physics features. Feature which seems like a bug one. Single token feature. Single token feature. When we limit the dictionary learning to use very few learned sparse features, the feature that emerge sometimes looks quite strange. In particular, the large number of high activation. We believe that splitting explains the phenomenon. Model hasn't learned a single feature firing on the letter P. Meta question about features is where they are universal. Yeah, So, we refer readers to do later works. Okay. Memorization. Okay, bro. Scaling is the most important work. Then scaling allows for dictionary learning. How can we recognize good features? Hmm. Scalability for analysis, algorithmic improvement to site, attention superposition, theory of superposition features. Okay. I guess I'm going to stop there the stream. Thank you for watching. We'll continue soon, very soon.